Hello again, this is Mr. Smith. Today we're talking about the mean value theorem. And before we get into that, let's just give a little example of what the mean value theorem really says. I'll give you like a little real life example. It's fairly easy. Let's say there's this dude. I don't know, we'll call him Dude. Okay, so there's this guy, his name is Dude. It could be a girl as well. And Dude lives, I don't know, 30 miles from school. Okay, he lives a real long way from school. And he leaves his house at 7 o'clock in the morning. And he ends up at school at 7:30. So, dude gets up, gets showered, brushes his teeth, probably eats something because, he's a healthy kid and wants to have a good start to the day. Gets all his crap together, heads out the door at 7, or gets in his car and leaves at 7, and ends up at school at exactly 7:30. What can we say about dude's speed? Well, most kids in my class will be able to say, well, it looks like he did 60 miles an hour because 30 miles in 30 minutes is a mile a minute, which is 60 miles an hour. But actually, we don't know that he did 60 miles an hour the entire time. And in fact, we're pretty sure he did not do 60 miles an hour the entire time because dude has to start off, and he's not going to start off doing 60 miles an hour right away. That doesn't make any sense. He's going to start off at 0 and speed up. And when he parks, he's going to have to slow down and park. So we know he definitely did under 60 miles an hour. But what we know is that he averaged 60 miles an hour, okay? So he averaged 60 mphs. Now, how do we know that? Well, to find average velocity, this is a formula from physics. You take your position at the end time. Okay, so this is going to be position at 7.5, 7.5 hours, 7:30. Subtract off your position, S stands for position in this case, at 7. Okay, so it's really your change in position divided by your change in time, which for us is going to be 7.5 hours minus 7. Now what that tells us is his position is 7.5, and position in this case we're going to measure as distance from home. So it's 7.5, 7:30. He's 30 miles from home because he's at school. Minus at 7 hours, 7 o'clock a.m., his position was 0 because he was at home, we're saying. Okay? And this is all hypothetical, I'm just making this up. Divided by 7.5 minus 5 is 0.5. And that's going to give us 60. Well, the distance is in miles, and the time is in hours, so he did 60 miles per hour. But this formula gives the average velocity, average speed, really. Velocity in this case. Well, speed as well because it's positive. But here's what the mean value theorem says. We haven't mentioned the mean value theorem. I'm just rambling on about this dude. The mean value theorem says if we know that his average rate of change was 60 miles an hour, then if a few conditions are met, and in this case they are, we know not that he did 60 miles an hour the entire time, but we know that at least once in his traveling, he must have been doing 60 miles an hour. At least once he must have done it. And if we really think about this, in this case, he actually had to at least have done 60 miles an hour twice. Because he started out slow, he would have to speed up to above 60 miles an hour to compensate for being below 60 miles an hour. And then once above 60 miles an hour, he'd have to come back below 60 miles an hour. So he'd probably have to go through 60 miles an hour twice. He might have done it more than once if he had a few red lights or something. He'd probably slow down, speed up, and all that stuff. But that's really all the mean value theorem says. If you know the average rate of change, in this case 60 miles an hour, then you know the instantaneous rate of change, his speed at any given second, must have been 60 miles an hour somewhere. Okay? So his velocity at some time, okay, I'm just going to call it time c, had to have been 60 miles an hour because his average rate of change was 60 miles an hour. And let's remember this, velocity is the derivative of position. Okay? Well, that's exactly what mean value theorem says. Here it is. And here's the conditions as well. If the first condition, a function is continuous on the closed interval from a to b, there's x values, they'll give you the x values in a problem most likely, like 1 to 5 or something like that. And the second condition is that the function is differentiable on the open interval from a to b. So it has to be continuous everywhere from a to b, including the endpoints, and it has to be differentiable everywhere from a to b, not including the endpoints. Now that doesn't mean it can't be differentiable at the endpoints, it just means it doesn't have to be. So it's a little bit looser of a restriction. Then here's what our theorem says. Then there must be an x value, and usually they call that c. Okay? There must be an x value where the derivative f prime at that point c is equal to this fraction, f of b minus f of a over b minus a. Now, f prime of c we can think about several different ways. Number one, That is the instantaneous rate of change. Instantaneous, that's how you spell that guy. Rate of change of f at x equals c. We can also think of f prime of c as the slope of the tangent line at c. At x equals c. Okay? So we've been doing that all year. It's the instantaneous rate of change. It's how fast the function's changing. And we also think of it as the slope of the tangent line at x equals c. In our previous example, we're saying s prime is velocity. So the instantaneous rate of change of position, which is velocity, must have been 60 miles an hour somewhere in there. Okay? We can think of this fraction over here, this f of b minus f of a over b minus a. He gets a special name. F of b minus f of a over b minus a. Well, that is the average rate of change. And you're going to want to memorize that. Average rate of change of f of x on the interval a to b. And in terms of slope, we can think of that as the slope of the secant line of f of x. Let me squeeze this in here. Of f of x on a to b. So the derivative doesn't need an interval, it just needs a point, an x value. In this case, we're saying that's c. Now we don't know what c is, but that doesn't matter. Usually the goal is to find out what c is. F of b and f of a we can find by plugging in b and a, which will usually be given to you. So the tangent line has a slope, that's f prime, and all you need is one x value and a function to find that. But the secant line, you need two x values and a function to find the secant line because it's a slope between 2 points. And that makes sense. If you look at f of b minus f of a, well, that's the same exact thing as y2 minus y1 over x sub 2 minus x sub 1. That's slope. It's slope between 2 points. That's all this thing says. And honestly, the value theorems in general, the intermediate value theorem, extreme value theorem, and the mean value theorem, are all fairly simple. It should make sense that if he averaged 60 miles an hour, that at some point in time, he must have done 60 miles an hour. There's nothing really crazy about that. The problem is when we turn it into all those math terms, it gets a little funky. So the first thing I'm going to do real quick is talk about these conditions. Why do we have these conditions? So I'm going to go ahead and erase all this. Okay, why are these conditions here? Well, I'm just going to give you an example to what happens if those conditions are not there. Is that okay? So number one, let's say the function wasn't continuous on an interval. Okay, well, if the function is not continuous, I'm going to make this very, very convenient for myself. Let's say it's not defined at a, so it's not continuous at a. Okay, so let's say we have a function that goes from, it doesn't matter what the curve looks like, here, and then it goes down to here. Okay, so let's say that's our a value, and here's our b value. Alright, now our goal is to find f of a minus f of b, and that's really where this thing breaks down. F of a minus f of b over, oh man, I did it backwards, I'm sorry. F of b minus f of a over b minus a. And you know what, we can actually give these values here. Let's say that we want to find the slope between 3 and, I'm just making these numbers up, 7. That's the power I have as a math teacher. I can just make up whatever I want. 3, this is 7, this is 3. Now, the problem is f of 7 is f of 3 is undefined. There's no point there. So this should be some number. This should equal something. And then we can set the derivative equal to it and find c. F of 3 is not a number, so we can't find the slope between these 2 points. Now you're like, well, there's a hole there, so we can find it. Well, true, you could use the value that should be there, but we need f of 3, and there is no y value for 3. There's nothing there. So this is not a number, and it doesn't work. Okay? So that's one example of why it has to be continuous. There's a bunch of other examples you can check out. I'm not going to worry about it right now, but that's one thing you should check. The function must be continuous. Second thing says that the function must be differentiable. Now, before we do an example of why it has to be differentiable, let's just take like a good example and show you what this thing is saying graphically. Okay, so let's say this is our curve from A to B. All right, we'll say this is actually we'll just use A and B here in this case, A and B, and let's draw what this means. Well, oh man, I divided this guy out here. This should be B minus A here. I erased him by accident. This number right here, again, I said is just a slope between point A and point B. All right. Well, the x value is A. The y value would be f of A, and f of B would be up here somewhere. Okay? It's just the slope between them. It's the slope of the secant line. Well, let's draw the secant line. The secant line goes through A and B, so it's got to look. I'm going to draw it in dashed line here. There you go. Slope of the secant line. That's all that is. Okay, you can actually find the secant line by finding the slope and then taking one of these points and finding the line that goes through there. You did that in Algebra 1. They give you 2 points. Here they are. A, f of A, B, f of B. Find the slope, find the line that goes through them. No problem. What the calculus is going on here is saying that somewhere on this interval, oh, I forgot to put that too. I'm falling apart here, kids. Tack this on the end of this guy. It must equal this, and C must be between A and B. Okay? The derivative has to equal this slope somewhere between A and B. And you can see in this case, if the slopes are equal, that means the lines are parallel. The tangent line and the secant line are going to be parallel. And you can see like maybe somewhere like right there, let's draw him in green, the tangent line is going to be parallel to the, whoops, my fault, to the secant line. Something like that, if it just touches it for a second there. Okay? And you can see that they are parallel. Let's go back up here. That's what mean value theorem says. Tangent line somewhere in the interval has to equal the secant line between the 2 points. Alright, now, if the function is not differentiable, that doesn't necessarily have to happen. So let's take a look at one that's a function that's not differentiable. We'll make this very easy. Let's say there's a corner in the middle somewhere, okay? Alright, so let's say, here's A, there's B. Now the slope between them is 0, okay? There you go. But nowhere on this interval is the derivative 0 because there's a corner. You can see on the left-hand side of that corner the derivative is positive, not 0. That's right here. Okay, and on the right-hand side of the corner, the derivative is negative. But it doesn't have to go through 0 because there's a corner there. If that was a smooth curve, like this guy, well, now you can see the secant line is 0. It's differentiable everywhere. And the tangent line up here is going to have a slope of 0 at the very top. That's a maximum.
When?
Yes, baby.
Dinner's ready.
Awesome, dinner's ready.
How much longer do you got?
Oh, I don't know. A few minutes.
Okay, that's fine.
Alright, baby doll. Alright, kids, dinner's ready. I gotta finish this up here. So, let's do an example. Okay? Again, never forget, all the mean value theorem says is that the function is continuous on the closed interval, differentiable on the open interval, and it could be differentiable in the closed interval as well. It doesn't matter. But it doesn't have to be differential at the endpoints. Then, when you find the average rate of change, which is this fraction, which is also the slope of the secant line, then that number, because it's going to be a number, the derivative must equal that number at some x value on that interval. That's all it says. Let's try an example. Okay, real quick. So let's say f of x is x squared. Okay, and our interval is from 1 to 5. And the question is going to say, find the value of c guaranteed by mean value theorem. And usually they'll write MVT because they're lazy and I'm lazy. Okay, so all we got to do is find out where the secant line is parallel to the tangent line. Well, the first thing we're going to do, we can write the formula out if we want. F prime of c must equal f of b, which is 5, minus f of 1, which is that. F of 5, I'm sorry, minus f of a is 1, so over 5 minus 1. Well, f of 5, all you do is plug f of 5, plug 5 in for x squared, 25. Minus, plug 1 in, you get 1, over 5 minus 1, and this is always going to be a number. Okay, as long as the function is meets the, as long as it's defined at the endpoints. Anyway, 25 minus 1 is 24, over 4 is 6. Okay, we got to find out where does the derivative equal 6. Well, the first thing, well, not the first thing, but the next thing we need to do now is find what the derivative is. The derivative of f of x is 2x. That's easy. But we don't want f prime of x here, we want f prime of c. So instead of putting x, we put a c. That's the only difference. You can put an x there as well, it really doesn't matter. To be honest with you, you're going to get the same answer. Must equal 6, and you can see that happens at 3. So, the tangent line at 3 is parallel to the secant line between 1 and 5. And now, mean value theorem doesn't tell you how to find c, it just says it's going to be there. Okay, so you're not really doing the mean value theorem here. You're setting it up and you're finding c. The mean value theorem just guarantees it's going to be there, as long as it meets those conditions. So let's say instead of them giving you x squared, let's say they gave you x squared, I'm going to squeeze it in here, over x minus 2. Well, now the mean value theorem doesn't guarantee us anything, because this function is not defined at 2, and 2 is in the middle of our interval.